More general than relation is shown with the help of a diagram in this slide. On the left hand side, you can see the instance space in which each dot will indicate one instance. On the right hand side, hypothesis space capital H is shown in which the hypothesis H1, H2 and H3 are moving from more general to more specific. H1 is indicating X1 as well as general values. H2 is indicating X1 and X2 and more general values. H3 is indicating X1 and some general values. In the diagram, it can be easily interpreted that H2 is greater than H1 because H2 contains more general attribute values. Again, H2 is also greater than H3. In H3, there are two constraints, but in case of H2, there are only one constraint. Hence, H2 is also greater than H3. But there is no more general relation between H1 and H3. Find S algorithm. Find S algorithm starts from the most specific hypothesis, that is all the null values, and generalizes it by considering only positive examples. Find S algorithm ignores negative examples. Negative samples where the concept value is no is not considered in Find S algorithm. As long as the hypothesis space contains a hypothesis that describes the true target concept and the training data contains no errors, ignoring negative examples does not cause to any problem. Find S algorithm finds the most specific hypothesis within the hypothesis space H that is consistent with the positive training examples. The final hypothesis will also be consistent with negative examples if the correct target concept is in capital H and the training examples are correct. Let us see what is Find S algorithm. The algorithm steps are as shown. First step is initialize small h to most specific hypothesis in hypothesis space, that is capital H. Second step is for each positive training instance X and in for each attribute constraint AI in H, if the constraint AI is satisfied by X, then do nothing. This means the attribute value and specific hypothesis value are matching together. We need not have to do anything else. Replace AI in H by the next more general constraint that is satisfied by X. We are replacing here with the question mark. Question mark will indicate any value is acceptable. Third step is output the hypothesis small h. Find S algorithm example. If you see the diagram, all the instance space and hypothesis space is listed over here. H0 will be the starting point in Find S algorithm. That will be the first hypothesis. All the values in H0 is considered null values. Then these null values are compared with the first instance, that is X1. Null is compared with sunny. Null means there is no value at all. So sunny remains as it is. Similarly, warm, normal, strong, warm, same are copied. Next, check whether it is a positive instance. Yes. H1 is compared with X2. Sunny is compared with sunny. Both the values are same. Hence, sunny is written in first place of H2. Next, warm is compared with warm. They are same. Same value is copied in H2. That is, next value will be warm. If you see the third value, that is, normal is compared with the high. Both values are not same. Hence, question mark is written. Question mark will indicate any value is acceptable. In this way, the algorithm will continue and all the hypotheses are written. In the iteration, the hypothesis will move from most specific to most general hypothesis. Unanswered questions by Findes algorithm. There are few questions for which there is no answers in Findes algorithm. Some of them are: has Findes algorithm converged to the correct target concept? Although Findes will find a hypothesis consistent with the training data, it has no way to determine whether it has found the only hypothesis in hypothesis space consistent with the data, or whether there are many other consistent hypotheses existing. We would prefer a learning algorithm that would determine whether it has converged, if not, at least characterize its uncertainty regarding the true identity of the target concept. The second question is, why prefer the most specific hypothesis? In Findes algorithm, there are multiple hypotheses consistent with the training examples. Findes will find the most specific out of them. It is unclear whether we would prefer this hypothesis over the most general one or some other hypothesis of intermediate generality. The next question is, training examples are consistent? In most practical learning problems, there is some chances that the training examples will contain at least some error or noise. Such inconsistent set of training examples can severely mislead Findes, given the fact that it ignores negative examples. We would prefer an algorithm that could at least detect when the training data is inconsistent and preferably accommodate such errors. Next question will be, what if there are several maximally specific consistent hypotheses exist? In the hypothesis capital H for the enjoy sport task, there is always a unique most specific hypothesis consistent with any set of positive examples. However, for other hypothesis space, there can be several maximally specific hypotheses consistent with the data. In this case, Findes must extend to allow it to backtrack on its choice of how to generalize the hypothesis.